Hello. In this video, we're going to look at how to factor trinomial quadratics in the form ax squared plus bx plus c. So not all of these are factorable, but when they are, our goal is to ultimately get it expressed as a product of two linear binomials. So the idea being I'm going to have four pieces here. So a plus b, let's say, and c plus d. Now when I multiply, factoring being the opposite of multiplication here, there would be four multiplications going on. So the three terms in my trinomial come from four separate multiplications. So what I note here is that in this example where I've got 5x squared, that 5x squared has to come from multiplying. So the quadratic term has to come from multiplying together the two linear terms. And 5x squared can only be the product of 5x with x because 5 is a prime number. So that works out nicely for us here if we have a prime number. The other thing I'll note, so in this context, I actually sort of have ax plus b and cx plus d. So my quadratic term comes from multiplying together the ax with the cx, whatever those end up being. The other thing, so that's the quadratic term. The other significant term is the linear term, or the constant term. So the constant term here is 8. 8 has to be the product of the two constant terms in my linear factors. So in this case, 8 has to come from b times d. But there's a number of different options here. So for example, I could have 2 and 4. I could have 1 and 8. I could have 8 and 1. Maybe I have -2 and -4. So there's a lot of different options here. And that's where that sort of middle term comes into play. Because in this instance, the linear term, the minus 14x, that comes from the product of b with cx and ax with d. So that term comes from two places. So what I'm going to note here is that if I multiply together the constant and the quadratic term, I get 40x squared. That's the same product I should get by multiplying together all of a, b, c, and d. The linear term comes in this case from AD plus BC. So all of those things together have to multiply to A, B, C, D, so which is in this case 40x squared. What that means is I'm looking for two things that I can split up, two terms that multiply together to be 40x squared, but that add together to be minus 14x. So for example, 40x squared could be the product of just x and 40x. But if I added those terms together, I would get 41x. That's not what I'm after. It could be the product of 2x and 20x. But again, that would not give me minus 14x. In fact, if I note, so 4x times 10x, that would give me 40x squared. But it's not, it wouldn't give me negative 14x. So what needs to change actually is I need minus 4x and minus 10x. So that minus 4x and minus 10x, that's what I get from these two outside and inside products. So knowing that I already have a 5x, what would I have to multiply 5x by in order to get either negative 4x or negative 10x? Now 5x times a whole number is never going to give me negative 4x, but 5x times negative 2 is going to give me negative 10x. And x times negative 4 is going to give me negative 4x. So these are two linear factors, which if I check the multiplication, 5x times x is going to give me 5x squared. 5x times negative 2 is negative 10x. Negative 4 times x is negative 4x. And negative 4 times negative 2 is plus 8, which does simplify to 5x squared minus 14x plus 8. So that seems like an awful lot of explanation to get to these two factors. But in the end, we can sort of shortcut this, and I'll actually show us some ways of organizing other than just filling in the pieces as I did here. So let's look at another example. Recall that the first thing that I really wanted to deal with was, I know I'm getting into two linear factors. Here, I know I'm going to have something x times something x equal 12x squared. I'm not as lucky as I was in the last case because 12 is not a prime number and I have a few different options here. My constant term is negative 3, so I'm a little luckier. It could be 1 times negative 3 or it could be 3 times negative 1. But I'm not going to jump to that at the moment. I'm going to jump to where I was when I said let's multiply the quadratic term times the constant term. So the quadratic term times the constant term is negative 36x squared. And now what I was ultimately looking for is I'm looking for two things that have a product, two linear terms that have a product of negative 36x squared, and they have a sum of positive 5x. So I can think about this systematically if it doesn't immediately come to me. 36 would be 1 times 36, or 2 times 18, or 3 times 12. 4 times 9 is where I'm going to find what I'm looking for, because the two terms that I'm looking for here are 9x and negative 4x. If I multiply 9x times negative 4x, I get negative 36x squared. If I add them, I get 5x. The 9x and the minus 4x have to be what I get when I do the outside multiplication and the inside multiplication. But ultimately, one of the ways I can figure out what these two factors are going to be is by organizing these in sort of the same sort of boxes we were using for multiplication, but I'm going to now work kind of backwards for division. Now I know that the result of my multiplication, when I multiply the two linear terms the two linear terms had to give me the quadratic term of 12x squared. And when I multiplied the two constants together, I have to get minus 3. And now I know what the two pieces of my linear term are. They are 9x and negative 4x. And ultimately, it doesn't matter which one I write where. So now what I'm going to do is I'm going to factor the greatest common factor out of each row and each column. So looking first at the first column, the greatest common factor of 12x squared and negative 4x is 4x. At the second column, the greatest common factor of 9x and negative 3 is 3. Now looking at the first row, the greatest common factor of 12x squared and 9x is 3x. And at the second row, the greatest common factor of negative 4x and negative 3 is just negative 1. This tells me that my two linear terms are 4x plus 3 and 3x minus 1. I read the row and the column of what I pulled out. And again, you could re-verify this. If I multiply the 4x with the negative 1, I get negative 4x. If I multiply 3 times 3x, I get 9x. When I multiply together these two linear terms, 4x times 3x does give me 12x squared, and 3 times negative 1 does give me negative 3. So ultimately, the two factors, I'll just rewrite it in nice factored form without all those lines everywhere. 4x plus 3 times 3x minus 1. All right, let's do that again with this next one. So I'm going to jump to the point where I multiply the quadratic term times the linear term and I get negative 10x squared. I'm looking for a product of negative 10x squared and a sum of negative 3x. So that is negative 5x and 2x. If I multiply them, I do get negative 10x squared. If I add them, I get negative 3x. So to organize this in the boxes, I've got my quadratic term in one upper left-hand corner. In the lower right-hand corner, I have my constant term. And then the two terms I've just chosen, minus 5x and 2x, in either of the other two boxes. Factoring by row and by column, between 2x squared and 2x, I have a common factor of 2x. Between negative 5x and negative 5, I have a common factor of negative 5. Between 2x squared and minus 5x, the only common factor is the x. And between 2x and negative 5, there are no common factors, so it's just 1. This means that the factorization here is 2x minus 5 and x plus 1. As you get more comfortable with these, you will no longer need to rely on the boxes. You may be able to just jump straight to the factors, and that's great. That's our end goal. But don't be afraid to use the organizational strategies as you need them. In this next instance, where I have a leading coefficient of 1, it is a little bit simpler because I know that this is going to be x and x as my linear terms. So this is a great example of where I might be able to do without the organizational boxes to start. I do still follow the same process. I'm looking for two terms that have a product of 17x squared and a sum of 18x. And that's obviously going to be 17x and 1x. Remembering that those need to come from the outside and inside multiplications when I'm distributing, I would have to multiply x times 17, for example, to get 17x, and x times 1 to get 1x, and they are both positive. So my factors are x plus 17 and x plus 1. And one final example. I can just jump straight to what I was doing. I can multiply 4x squared times negative 54. I'm going to get a fairly large number, though, and I'd really rather not have to check the factors of a fairly large number. But what I note here is I can't forget the factoring we've learned before. In this case, I do have a common factor in all of these terms. 4x squared minus 6x and minus 54 are all even. So I can start by dividing out a 2. So I have a factor of 2, and then 2x squared minus 3x minus 27. This makes the ensuing factorization a little bit easier, because now I'm dealing with smaller numbers. 2x squared times negative 27 is negative 54x squared. In order to get a product of negative 54x squared and a sum of negative 3x, I need to use negative 9x and positive 6x, which means that I'm dealing with 2x squared as my quadratic term, negative 27 as my linear term, negative 9x and 6x as my two linear terms. Oh, negative 27 was the constant term, sorry. Between 2x squared and 6x, I have a common factor of 2x. Between negative 9x and negative 27, the greatest common factor is negative 9. Between 2x squared and negative 9x, the greatest common factor is just the x. And between 6x and negative 27, I can factor out a 3. Which means that I have the 2 that I already had out front. That is still one of the factors. Then I have a factor of 2x minus 9 and a factor of x plus 3. So those are the factorization, or that is the factorization of 4x squared minus 6x minus 54.